So folks, after that somewhat lengthy intro to calculus of vector valued functions, armed with that big result from that last video, we're able to carry over a lot of our work from one variable calculus to the individual components of a vector valued function. So let's go ahead and put that into practice. If we're asked to evaluate this limit here, we've got the limit as t is approaching 5 of the function r of t. And so what we just said by that big result is that's equal to the limit as t approaches 5 of the function t in that first coordinate function, the limit as t approaches 5 of t minus 2 all over t squared minus 4 in that second component, and the limit as t approaches 5 of the natural log of t in that third component. And then we can evaluate each one of those limits using one variable calculus, and so that's just 5. That would be 3 21st, and that would be the natural log of 5. And there we've evaluated that. That wasn't a very interesting example because there was nothing kind of interesting happening in the graph of that vector valued function at the point where t was 5, and evaluating the limit at t equals 5 was the same thing as just simply evaluating the original function at t equals 5. That's because, and we've not carried this idea over yet, but that's because r of t is continuous at t equals 5. So let's look at a place where r of t is not continuous, namely at the value t equals, and careful folks, this should be a positive 2. I'll fix that in your handout. So if we look at the limit as t approaches 2 of r of t, what we'll need to do is we'll need to look at it'll be a vector valued function, and we'll need to look at, if it exists, and we'll need to look at the limits of each of the individual components. So if we look at the limit as t approaches positive 2 of the function t, well, that's just 2, so that'll be 2 there. And if we look at the limit as t approaches 2 of the natural log of t for that third component, that's just the natural log of 2. And that was really just using that direct substitution property that you learned in Calc 1. But the last part, which is kind of the interesting part and the reason for this example, is to look at that middle component. And if we look at the limit as t approaches 2 of t minus 2 all over t squared minus 4, remember what we had to do is we had to give a function that agrees with this function everywhere except at the limiting value. And a function that agrees with this function everywhere except at that limiting value is just the function 1 over t plus 2, where I factored out the denominator and canceled those like factors, and so we get the quantity 1/4. And this is more like that original picture that I showed you, where we had some vector valued function and we had some hole in that vector valued function. And what we're saying is as we take vectors, as we take t values getting closer and closer to, in our case, it was the number 2, and we could do that from either direction, we saw that the vectors are approaching this red vector here, even though the vector valued function isn't defined at t equals 2. And that's what we saw in this example here. But we did the evaluation of it. We did all the work relying on all of the Calc 1 knowledge that we have. Okay, so let's go ahead and do the last one. If we look at the limit as t approaches 0 of r of t, that limit does not exist. And the reason why is because the limit as t approaches 0 of the natural log of t, that limit from one variable calculus, that doesn't exist. And even if, in fact, I'll change this for your notes. I'm going to put from the right here, and from the right here, and from the right here. Even if we did that from the right, this limit is negative infinity, but the entire vector doesn't exist because, you know, even though the limit, we describe it as negative infinity, that limit doesn't exist, and so this limit doesn't exist. Okay, folks, so let's go ahead and finish this out, and now let's do some calculus. So here I've got a velocity vector given by these three components functions here. We could see that, you know, f of t is 3, and g of t is t, and h of t is 3t squared. And this represents the velocity of a particle in meters per second at any point in time. And suppose that when t is 2, we're at the position 555. That's like an initial condition that we'll need for one of these later questions. So the first thing we're asked to do is we're asked to find the object's acceleration vector function. Well, the acceleration vector function is simply the derivative of the velocity vector valued function. And as I implied above, and we'll talk about this more in class, that's going to be just equal to the derivative of each of the component functions. So we've got the derivative of 3, comma, the derivative of t, comma, the derivative of 3t squared. And so the acceleration function is just 0, 1, 6t. There's the acceleration function for this object, this particle that we have moving in space. And what we see is that the whole reason why this worked is because we were able to say that the derivative of a vector valued function is simply the derivatives of each of the component functions, provided each of those derivatives exist. So moving on, let's go ahead and find the object's position as a vector function. And so let's go ahead and we'll represent that as s of t. So we'll say that s of t is equal to the antiderivative of the velocity function. And that knowledge, that relationship between position and velocity, comes from our knowledge that we've already gained from Calc 1. And so how do we take an antiderivative of a vector valued function? Well, what I said before is, everything comes down to doing it component-wise. Careful, folks, Calculus 3 has a lot more than just working component-wise, so please don't get complacent after today's lecture. But what we can do is we can take the integral of 3 dt and the integral of t dt and the integral of 3t squared dt. And notice we represented that component-wise. And then what do we do when we get this? Well, let's see. This would give us 3t, and then we'd have a constant here. And in Calc 1, we just put a constant there. What I'd like to do is put a subscript of 1 there, and you'll see why in just a moment. When we take this antiderivative, we will get 1/2 t squared for its antiderivative, and I need to put a constant there, so I'll put c2. And when I take this antiderivative, I get t cubed plus a constant. Now, notice that I have a sum of vector components here. So usually what we will do, folks, when we do this is we'll just go ahead and take the antiderivative, ignoring the constant momentarily, and then rewrite this and then say that this is added to some constant vector c, where c is the constant vector c1, c2, c3. Okay. So this part right here, what we're doing right here, that should seem a little bit new to you. Maybe you haven't done, we probably haven't done anything like that. And now let's go ahead. We need to, just as you did in one variable calculus, we need to go ahead and figure out what that constant is. Well, we're told that s of 2 is equal to the vector 5, 5, 5. So if we go ahead and plug 2 into this function, we should have that 5, 5, 5, this vector, needs to be equal to 6, comma, let's see here, we take 2 and square it, we get 4, divided by 2 is 2, and if we take 2 and cube it, we get 8, plus the constant vector. Sorry, folks, I ran out of room there, so I'll just add it there. Sorry about that. And so notice this enables us to figure out what C1 is, C2 is, and C3 is. So we figure out that C1 would have to be a -1 in this case, because if I take 6 and add it to the first component of C, I need to get the number 5. And we'd find that C2 would be the constant 3. And we'd find that C3 would be the constant -3. And so now we can go ahead and actually give s of t as a full vector valued function. It would be 3t minus 1, comma, 1/2 t squared plus 3, comma, and t cubed minus 3. So that's how we evaluate that. Okay. So finally, folks, we've got one more example, and that's to evaluate a definite integral of that velocity function. So this is going to be the integral from 0 to 1 of v of t dt. And again, everything gets to be done component-wise. Again, folks, please don't get complacent in this class. This particular topic is relatively straightforward because we get to just work things component-wise. Okay? So what I'm going to do is I'm going to say that that's equal to, provided these antiderivatives exist, or provided these definite integrals exist, the integral of, I think we had a 3 dt plus, or comma, since we're using this notation, the integral from 0 to 1 of, I think we had t dt, comma, and then the integral from 0 to 1 of 3t squared dt. Folks, let me just double check my vector. So we had 3t and 3t squared. Great. Okay. So if we evaluate this, we're going to have 3t evaluated between 0 and 1, 1/2 t squared evaluated between 0 and 1, and t cubed evaluated between 0 and 1. And we perform each of those operations, and this gives us 3, 1/2, and 1. And that represents, what would that represent? That would represent displacement of the object between the first and, or between the 0 and 1. So between time t equals 0 and t equals 1. It's not necessarily how far this object traveled, but it's the, we would have, maybe this object's curve, and this is not correct at all, maybe this curve looks something like this in 3 space. And here we are at here's the position at t equals 0, and here's the position at t equals 1. And if we found the difference between those two vectors, that would tell you the net displacement between time t equals 0 and t equals 1. And there we have it. Okay. So folks, that was a long example, but hopefully you see how some of your Calc 1 work is going to carry over nicely into this course. Please take a look at this, folks, and let me know if you have any questions. Thank you very much.